Right, ladies and gentlemen, let's continue with Chapter 7. We are making use of the textbook of Cengel and Ghajar, and Chapter 7 is on external forced convection. In terms of convection, you'll see that we're going to do quite a number of chapters on it. We've started with the fundamentals of convection in Chapter 6. Chapter 7 is on external forced convection. The next chapter on internal forced convection, and the chapter after that will be on natural convection. Specifically, external forced convection, where is that important? And that is addressed in paragraph 7.1 in your textbook. Examples are where we are interested in the flow and heat transfer over solid bodies, and that would include cars, power lines, trees, underwater pipelines, the lift developed by aeroplane wings, upward draft of rain, snow, hail, and dust particles in high winds, and the cooling of metal or plastic sheets, steam and hot water pipes, and extruded wires. So those are typical examples of external forced convection. So paragraph 7 is external forced convection. And I'm going to specifically look at drag and heat transfer. And the drag part would be a quick revision of your fluid mechanics. Going back to fluid mechanics, the drag force is equal to a drag coefficient multiplied by a half rho v squared and an area like that. Where do we get this coefficient from? Well, from experiments. We would go and do experiments on which we would measure the drag force, and we would divide it by half rho v squared and the surface area. So experimentally. And if you do many of these experiments, you're going to find that the drag coefficient is a function of the shape of the geometry. It will be a function of Reynolds number and surface roughness, epsilon divided by d, and not only the shape, but also the orientation of the shape. So it might be the same shape, but by just changing the orientation, you can change the drag coefficient. Now this drag coefficient, CD, is a function of two forces. It is actually the pressure forces as well as the shear forces. So the sum of the pressure forces and the shear forces would give us our drag, and from it we can determine the drag coefficient. So if you're interested in getting the drag of an aerofoil or any types of geometry, then you have to be careful that if you go and look for the coefficient, which one it is, because you need to take into consideration the pressure one as well as the shear one. And in many cases, they are not given together. Let's look, for example, at the pressure force. The pressure force, you're going to determine that from experiments. And with the experiments, you're going to have this velocity, V infinite, and we call that the upstream velocity, or the approach velocity. So in terms of an aeroplane that has been propelled through the air, the aeroplane wing will fly at a velocity v infinite, but we can get exactly the same effect if we kept the aeroplane wing in a wind tunnel and the wind is being forced over this aeroplane wing. Now, if you are very good with experiments and you go and put many, many holes in the surface and you connect it to a manometer so that you can actually measure the pressures, and you go and you plot the pressures, you're going to get a result something like that. So that would be the pressure multiplied by the area. And that would be at the top side, and yet at the bottom, you'll get something similar. So schematically, we can actually look at all those pressure forces, and you can go and determine the total force, F total. The total force on that aeroplane wing. However, it has two components. It actually has a component there and a component there. And this component will be FL, and FL would be the lift force. So that's the important one, keeping the aeroplane in air. And this one, this one here is the drag force, FD. The lift force and the drag force. So the drag force is parallel to the free stream velocity, and the lift force is always perpendicular to the free stream velocity. Now, if you get these two components, you shouldn't now think these forces actually represent everything, the pressure forces and the shear forces. What you also need to do is on that same aeroplane wing, you need to go and measure all the velocities around it. And these gradients that we have there is the shear stresses. The velocity gradient multiplied by the viscosity, and this would be the drag because of shear stresses. Thus, the total force and or the drag coefficient is actually can be split into two components. The shear stresses, FD, we can say is then equal to FD, the pressure forces, plus FD from the shear stresses. Now, if we do the experiments and we go and plot the experiments of CD, and this is, let me use another color. This is the leading edge of the aeroplane wing, and that is the trailing edge, and that is the distance like that. So that would be where x is equal to 0, and that is where x is equal to L, the total length of the aerofoil. And if we go and put everything together, we can actually develop a graph, something like that, that would now show all these forces. And because we have done all mathematics, you're going to integrate it so that you can actually determine the average. And as engineers, in many cases, we are interested in getting the average. So this drag coefficient can include the total body, and or it can be given or determined at a very specific point. For example, maybe a quarter of the, from the chord, you can go and determine it at that specific point. Now in fluid mechanics, you would also know that if you look at, for example, the flow around a cylinder, then the flow doesn't, in many cases, follow the geometry perfectly. It would separate from the body. And here at the back, we can have very complicated flows, and we would call that the flow separation point. This is where flow separation occurs, and this would typically be the wake of the body. And every unique geometry will have a different flow field, and in many cases we would like a wake, while normally in something like aerodynamics you wouldn't like a wake and you do not want the flow to separate. Now, because this can be very complicated, what we are first going to do is we are going to start with a flat plate. Because if we can understand what happens on a flat plate, it is easier to take the next step for a geometry that's a little bit more complicated. So, in terms of, if this is the flat plate, we will draw it like that. And that would be the free stream velocity. And if we would go and measure the drag on a flat plate, then as I've done with you now previously, this would be equal to the pressure drag as well as the skin friction drag or the shear stress drag. Now, for the case of a flat plate, this component is equal to 0. So it's a very, very simple case. If, however, we would take the flat plate, and that is the free stream velocity, if we would change the orientation of that flat plate so that it is perpendicular to the free stream velocity, then this drag force is going to be one or other pressure drag and a shear drag, and in this case, this component, again, in this case, is negligible in comparison with the pressure drag. Okay, so coming back to the drag coefficient, it's a function of shape, orientation, but also Reynolds number and surface roughness. If we now jump to heat transfer, before we get to heat transfer, if we now just look at the pressure or the drag force, then we've said it is a function of Reynolds number, surface roughness, etc. The moment we get to heat transfer, then we are not interested in the drag force or the CD coefficient. We want to get the Nusselt number. And the Nusselt number is always equal to a constant multiplied by Reynolds to the m and Prandtl to the n. And the Reynolds number, of course, is equal to rho Vd divided by the viscosity, and the Prandtl number is equal to the Cp multiplied by viscosity divided by the thermal conductivity. If it's air, and I ask you to go and get the properties for me, you can go to your textbook and you can go and look for the properties in air. However, you're going to see the properties are a function of temperature. So if we've got a problem of external forced convection and we would like to look at the heat transfer, we need to decide at what temperature should it be. Normally, if this is maybe a body and it's at a temperature Ts, or it might be a body like that, and that is the temperature Ts, and that is the free stream velocity and temperature. What we normally do is we define what we call the film temperature. And the film temperature is then the average of the wall temperature or the temperature of the surface plus the free stream temperature divided by 2. Now, just as we previously would say the friction coefficient, typically with this one, or the drag one, can be determined by the integration of the local values, Cfx, dx. In a similar way, we can determine the heat transfer coefficients with experiments over the total body length from 0 to L of local heat transfer coefficients dx. What am I trying to say? Well, I'm trying to say that if we've got any type of body from 0 to x, and that is maybe the length of the body, L there, and we would like to know the heat transfer coefficients, and we plot Hx, x means it's a local, the local values, then with experiments we are going to determine values like that, but as engineers we are typically interested in getting the average value. So we would do the integration and we would divide it, and we would divide by length, as indicated here, to get to the average value. And then we can write that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the temperature of the surface minus the free stream temperature. And this would then be the heat transfer rate for external flow. For external flow. Typically, all the flows that we're going to consider in this chapter. If the heat transfer is through an internal geometry, so that it's internal forced convection, then the heat transfer rate would be equal to the temperature difference between the outlet temperature minus the inlet temperature. So this is for internal flow. So external, if this is the body, that is the flow going externally over it, with internal flow, if this is the body, that would be the inlet temperature, and that would be the outlet temperature. And what we normally do, it's not like in thermodynamics, we would always choose the highest one first. So in many cases, the heat transfer might be in that direction, but in other cases, it might be in that direction. So we just normally use the highest temperature minus the lowest temperature to indicate the temperature difference. Paragraph 7.2 is now for parallel flow over a flat plate, and some of it is a little bit of revision that you've done in fluid mechanics. Fluid mechanics is a flat plate. If that is the free stream velocity, and that is the coordinate system of x and y, then we know that the boundary layer thickness will increase up to the point of transition. The transition area is quite problematic in many cases, and then it will have another type of form for the turbulent flow. So this flow regime is known as the laminar flow regime. That is the turbulent flow regime. And this is called the transitional flow regime. Transitional flow regime between the laminar flow and turbulent flow. Where the flow would change from laminar to turbulent or transition, we will call that distance the critical distance, the critical length, XRC. And this value of XRC is a function of the surface geometry, again the surface roughness, the upstream velocity, the surface temperature, and the type of fluid that is being used. So all those things will play an effect to get or to know what this distance is, and needs to be taken into consideration with determining the thickness of the boundary layer in laminar flow and in turbulent flow. Remember, the boundary layer thickness means that that distance there, delta, that is where the velocity is 99% of the free stream velocity. And again here exactly the same. That distance is the boundary layer thickness. We've done it previously. And the boundary layer thickness is where that velocity is 99% of the free stream velocity. What we also do on a flat plate is we define the critical, or the Reynolds number, sorry, not the critical one, the Reynolds X. What does X mean? It means local. And it can be written as the density multiplied by the free stream velocity multiplied by X divided by the viscosity, or in terms of the kinematic viscosity, if we want to use less terms, we can write it as Vx divided by the kinematic viscosity. And the kinematic viscosity, of course, is equal to the normal viscosity divided by the density. So if we look at a flat plate, it means that the Reynolds number, X, the local Reynolds number, X, where X is equal to 0, is always equal to 0. The Reynolds number at the leading edge is equal to 0, because it's the local value, and it will then increase as we go downstream with the plate or the geometry. So it means that the Reynolds number, if we plot it from 0 to L, of the local Reynolds number, would typically do something like that. It would be 0, and then it will increase as a function of x up to the length of the body. Now, this point of transition is a very important point to know about. And for a flat plate, when would the transition occur? At what Reynolds number? Anybody that can tell me? How much? 2,300. You all agree? Reynolds number 2,300, you're all wrong. Okay. It's very important. This critical Reynolds number depends on the geometry. You're right about 2,300, but that's for a tube. For a flat plate, that is not the case. For a flat plate, it is approximately 100,000, and in many cases, it can go up to 3 million before transition would occur. Now, because we do not want to use two different values in this course, we are going to use this value of 100,000 to be consistent. The 2,300 is correct, but take note, it is for a tube. So every body has its own transition Reynolds number. If you would now get into the wind tunnel, we can also determine your transition Reynolds number. And it will not be 2,300, and it will also not be 100,000, 1 multiplied by 10 to the 5. It will be a different value. And for those of you who are so privileged to have a Ferrari, and you do it with a Ferrari in the wind tunnel, and you would use a Hilux bucky, you get two different Reynolds numbers, critical Reynolds numbers. So, in general, we would use, not one, ladies and gentlemen, 500,000, 5 multiplied by 10 to the 5. So this Reynolds number of 500,000, if it's less, then we are going to say the flow is laminar. If it's more than 500,000, we will say that the flow is turbulent. And if the flow is laminar, we've already looked at the derivation, then the boundary layer thickness is equal to 4.91 multiplied by x divided by Reynolds x to the half. While for turbulent flow, it would be equal to 0.38x divided by Reynolds x to the fifth. So again, if we go to the leading edge of the plate, the Reynolds number is always equal to 0. Therefore means that the flow regime at the leading edge is always laminar. Okay. Then we can also determine the local skin friction coefficient, which is equal to 0.664 divided by Reynolds x to the half. For that one, and if it's turbulent, it is equal to 0.059 divided by Reynolds x to the fifth. Take note, this is the local value. For laminar flow, we can also get the average value. How can we see its average? The fact that it doesn't have an x. The x indicates a local value. Like that, it indicates we do the integration and we get the average value over the total body, and that is equal to 1.33 divided by the Reynolds number, take note, based on the length of the plate, to the power of a half. And for turbulent flow, CF is equal to 0.074 divided by Reynolds L to the fifth. Now, if you are awake, you will see there's a problem here. And what is the problem? The problem is, in this case, if we look at a flat plate of maybe 200 millimeters, and we would do measurements on it, we can get the CF value of the total length as long as everything is laminar. So if the flow velocity is low enough that we do not get the transition, and it's always laminar, then we can get the total skin friction drag like this, which is then also the total drag, because we've said that the pressure drag is equal to 0. However, if everything is turbulent on the total length of the plate, so let's suppose that is the plate, and now it is 400 or 500 millimeters, is it possible that everything can be turbulent on the plate? It cannot, because the leading edge is always 0. Therefore, what normally happens is the boundary layer starts to develop until we get to turbulent flow, and the rest of the flow, so that part would be laminar, and this part would be turbulent. So you can see there's a problem here, and the problem is you're going to ask me, well, okay, we see there's laminar, everything cannot be laminar, so when do we use this equation? Well, the answer is it depends on your discretion, on your good engineering discretion. If this plate is of length, where this is about 50% of the plate, then I think you would agree with me that it's not such a good example. However, if the application is of such a nature that this is only 10% or only 5% of the length of the plate, then we will say, there's no problem between good friends. We are going to make the assumption that everything is turbulent. So it's an engineering decision. So that's turbulent, that's laminar, but this equation assumes everything is turbulent. Now we can go and take into consideration the first part and the second part, typically by saying that CF is now equal to 0 to L, and we would do the integration from 0 to the critical distance of CF of the laminar part dx, plus we do the integration from the critical length up to the total length L of CF of the turbulent part dx, and we would divide everything by the length. Then we get over the entire plate, we can get an equation. It's just a little bit more complicated, which would say it is equal to 0.074 divided by the Reynolds L to the fifth minus 1742 divided by Reynolds to the L, and this equation would then be valid for everything from 500,000 to less than 10 to the 7th. And this would then take into consideration the laminar part. So like that. That is laminar, and that is turbulent. Take the laminar part into consideration. Now this is for a smooth tube. If it is a rough tube, a rough surface, sorry, not a tube, a flat plate, a rough surface, then Schlichting has determined that the friction coefficient is equal to 1.89 minus 1.72, the log of epsilon divided by L to the minus 2.5, equation like that. And you would ask me, but when do I consider a plate as smooth and when as rough? Well, almost all plates that you can buy in industry, all sheets, copper or iron or whatever it is, will normally be smooth tubes or smooth surfaces. Normally you have to go through lots of trouble to make it actually rough. Now this was actually, again, also quite an issue in the aeronautics industry with aeroplane wings. Coming back to this thing where we have flow separation. Not all aeroplane profiles actually are designed that there is no flow separation. In many cases there is flow separation. But again, with the design of it, it actually all started with considering it as a flat plate, and Prandtl did most of this work. The thing with a flat plate is it did cause flow separation. If there's an angle of attack, typically like that, then the boundary layer will grow, but then at the stage we will have some flow separation. And this flow separation can actually be controlled by changing the surface roughness. By making the surface rougher, you can actually prevent the flow from separating. At an earlier point, you can actually move it downstream. So a lot of work has been done also in this for different types of geometries. Now that is a summary of the fluid mechanics part. A similar summary we can do for the heat transfer part. Reynolds critical, for laminar, and for turbulent. For laminar, when the Reynolds number is smaller than 500,000. For turbulent, when it is larger than 500,000. So if it's laminar, then the local Nusselt number is equal to 0.332 multiplied by the local Reynolds number to the 0.5 Prandtl to the third. If we look at this, we can immediately see an irritation here. And the irritation is it gives us a local value. And if we get local values, we have to go and do a lot of work because we have to determine the values everywhere on this flat surface and then do integration. Well, fortunately, that has been done for us, and the average Nusselt number can be determined as 0.664 multiplied by the Reynolds number based on the length of the plate to the power of 0.5 Prandtl to the third, and this equation is valid for all Prandtl numbers larger than 0.6. So most gases and most liquids can be taken into consideration with that equation. For turbulent, there's also a local value, which can be determined from analytical work as equal to 0.0296, Reynolds x to the 0.8, Prandtl to the third, and the average Nusselt number for turbulent flow is equal to 0.037 multiplied by the Reynolds number based on the length 0.8 Prandtl to the third. So in general, what these equations actually tell us is that if we go and plot the local skin friction coefficients of drag, then that is typically what's going to happen. This is in the laminar flow regime, that's in the turbulent flow regime, and that would be in the transitional flow regime. So the skin friction drag would decrease downstream. When it goes to transition, it will increase almost an order of magnitude, and when the flow is turbulent, it would decrease. Now, the very interesting thing is that if we go and plot the heat transfer coefficient for over the total length L, there's the heat transfer coefficient, and if we plot it on the right scale, the results are very similar. That's the heat transfer results, and that is the CF values. The scale in terms of this value, which is maybe 0.5 here, might not be 0.5 there with the heat transfer coefficient, but the general curve of the two are exactly the same, and again it shows the Reynolds analogy that we've done with the previous chapter between fluid mechanics and heat transfer. Ladies and gentlemen, thank you very much, and then I'll see you again on Thursday. There's a question here.